Okay, so yeah, the next speaker is Andreas Wipf, who just raised the last question, and from Jena, and he will talk about inhomogeneous phases in the Gross-Neveu model with a finite number of flavors. And so now we are, I guess, moving from continuum theories to lattice.
Hello. No, thanks for inviting me. Can you see my slides?
Yes.
Perfect. Perfect. Yeah. Okay. So we shift gears a little bit in the sense that we are going on to the lattice first, and second that we lower the dimension of space-time. But let's slowly go into that. So I will talk about the inhomogeneous phases of the Gross-Neveu model. And the main point is that we are looking at the model at a finite number of flavors. And the motivation I will give in a moment why we are interested in that. So this was a work in collaboration with Julian Lenz from Jena, Lauren Panullo, and Mark Wagner from Frankfurt, and Björn Wellegehausen from Jena again. The first three, I think, are listening to this talk. And actually, Mark is giving the boring talk, I guess. Yeah. Okay, so this is a menu. I will talk a little bit about relativistic Fermi theories, also from a lattice point of view. The inhomogeneous phases of the Gross-Neveu model, also beyond mean field type approximation or large N approximations. And finally, we'll talk about very new results on the baryon number and the baryonic crystal in this type of models. Okay, so the models we are talking about, we have seen them many, many times, are of this type. So we have usual Dirac term plus a 4 Fermi interaction, and psi contains NF number of flavors. Now there are various motivations to study the models. One motivation we have heard many, many times is, of course, you would like to mimic the chiral sector of QCD. Then we will study John type models as effective theories. But there are, of course, also very, very relevant motivations coming from solid state physics to study these models in 1 and 2 space dimension. And that's actually what we are doing. So they are under intensive studies actually in the solid state community, slow energy approximation of certain models for example, graphene and the like Dirac type materials. So this is the type of model we have in mind, and I didn't specify what is exactly the 4 Fermi term. Most of the time I will talk about the Gross-Neveu, but actually not only. So again, let me be extremely short on this part. We have seen it many, many times. So it has been also argued or discussed that there may be a crystalline phase at the intermediate values of the chemical potential at low temperatures. Unfortunately, this part of the phase diagram is not really reachable with simulations, with first principles. And the main reason is, of course, a complex fermionic determinant. Now, there have been many, many efforts in the last years improving the situation, and we will hear more about in this workshop. Well, it started off with a sort of Taylor expansion, very small mu. At the moment, people are working intensively for 4 or 5 years on complex Langevin. More recently, the simple method. There are obviously efforts about dual variables and so on. Well, we have to see. At the moment, we are far away from this part of the phase diagram. Now, then you can, of course, resort to some sort of effective model building for the chiral phase transition, for example, some mean field type approximation, gradient expansion, the Ginzburg-Landau analysis, we just heard about it, functional methods to include some fluctuations. Or you can do something else. You can study gauge theory without the sign problem, where you can really do simulations at large densities or intermediate densities. The prominent examples are the SU2, which has no sign problem if you have an even number of flavors, or the G2 gauge theory, which actually we have studied some years ago. So most of the time I say that I'm talking about the Gross-Neveu model, which is a sort of a cool cousin of the Journal-Lassine model. It has a bit less symmetry. So you have this scalar-scalar channel. Here's a scalar-scalar interaction. And of course, we include a chemical potential. And we studied this model on the lattice with chiral fermions in 1+1 dimensions and in 2+1 dimensions. So let me say some more general results about 1+1 dimensions. So this describes certain polymers, for example, and other structures. Let me not go into that. It is also some sort of dimensional reduction if you start with a 4-dimensional theory and switch on an extremely strong magnetic field. So that in this model, psi bar psi is an order parameter for the Z2 chiral symmetry breaking. And in 1+1 dimension, lots is known, of course. If there's one flavor, then there's no spontaneous symmetry breaking. Actually, it's a conformal field theory in the massless limit. If NF is going to infinity, then there is spontaneous symmetry breaking of chirality. And actually, there's an inhomogeneous phase, and this is the main topic of this talk. In between 1 and infinity, the theory we know is asymptotically free. It's an integral system, but there are no really first principle results at finite chemical potential and finite temperature. In 1+2 dimensions, again, there are of interest in solid state physics. And this theory is non-perturbative. It's perturbative, it's non-normalizable, but of course we know it's normalizable in the large N expansion. It's one of the most simple realizations actually of an asymptotically safe field theory. And it has been also studied from this point of view actually by the group of Holger Gies, in particular in Jena. We know lots about these 4 Fermi theories in 3 dimensions, the fixed point structures in particular. Now, in this case, psi bar psi is an order parameter not for chirality, which doesn't exist in odd dimensions, but for parity. So we expect that for all number of flavors, there's spontaneous symmetry breaking for if you have a scalar-scalar interaction. I should mention, because this has been also sort of included in the previous talk, the vector-vector interaction in the Turing model situation is completely different. I mean, there was a long question, what is the, so at one flavor there's a breaking, for infinite number of flavors there is no breaking, so there must be a critical number of flavors where above which there is no breaking of parity anymore. It has been 30 years of efforts to find this critical value, and it sort of settles down the last 3 years, and actually we were heavily involved in these efforts. But anyway, that's besides the theme today. Okay, so this is our Gross-Neveu model, and of course we know we can get rid of the 4 Fermi theory by introducing an auxiliary field, integrating over the fermions, and then we are left with sort of a functional integral over this auxiliary field in the Gross-Neveu model with the effective actual comprising the log determinant of the fermionic operator containing, this is the operator on the top line, and of course the usual sigma squared from the bosonization. Now, what we often do in the large N expansion, we are allowed, of course, to use the saddle point approximation if the number of flavors goes to infinity. And then this partition function is just determined by the minimum of this effective action given here. So then it really boils down to understand the determinant of this operator containing this sigma field and the chemical potential. Now, if you assume translation invariance, then you assume sigma to be constant. Then it boils down to calculating the effective potential in various dimensions, this chemical potential, finite temperature, and we know how to do that. And you get this type of phase diagram. This is a phase diagram we have seen before, essentially in 1+1 dimension, and this is a phase diagram in 2+1 dimension. So what you find is a second order phase transition going up to this Lifshitz point, and then it continues with the first order transition. And well, the last 20 years, we have realized that, well, 25 years, that this is not the end of the story. Indeed, this first order phase transition goes away if you include inhomogeneous condensates. And what you get instead is a 2 second order line and an inhomogeneous phase, a third phase besides the symmetric phase and the homogeneously broken phase. So in a sense, the first order transition with metastable states sort of goes away, and some sort of a local phase separation, which goes into a inhomogeneous phase. Now in 2+1 dimension situation is different. All the way down, it's a second order phase transition, and it's only a first order phase transition at t equals 0, and the critical mu actually is 1 in 3 dimensions. The situation is different. There is no Lifshitz point at any finite value of the temperature, and you may get back a similar structure as in 2 dimensions, which may be relevant for building up an inhomogeneous phase by switching on a magnetic field. Then you also get actually many first order phase transition here for very low temperatures due to the Landau level occupation. So then in coming back to 1+1 dimension first, Michael Thies and his collaborators worked on this system for many, many years. And this is really a beautiful work. They were able to analytically solve the renormalized gap equation. So this gives them for inhomogeneous condensates. So this then gives an exact solution for NF at infinity. And most of the calculations have been done at L equal to infinity. And maybe we hear more about it in the next talk at finite length. Okay, so the condensate and the Gross-Neveu and NGL model are given by elliptic functions. By a nice inverse scattering method, they really could prove that these are exact solutions of the gap equation. Now, this inhomogeneous condensate, of course, breaks translation invariance. And so we would expect that there are massless Goldstone excitation, because translation invariance, this breaking is a breaking of a continuous symmetry. And of course, there should be some discussion in 1+1 dimension how this is possible and so on. There shouldn't be massless Goldstone excitations. Again, that's a very interesting story, which we can discuss later on. So anyway, the way out here is that this no-go theorem in large N doesn't apply. So there may be Goldstone excitations even in 1+1 dimension if NF goes to infinity. But then the question arises, of course, if you have to resort to NF going to infinity to get rid of the usual no-go theorem, whether there is such a breaking of translation invariance at a finite number of flavors, or of course, if you go beyond 2 dimensions, at least in this class of models. And again, I may say more about it later on. Okay, so the question then is, are there inhomogeneous condensates in these Gross-Neveu type models for a finite number of flavors? And in higher dimensions, if we include all possible fluctuations, not making any sort of mean field type approximations. So to understand the simulation result, let me shortly recall what we know about the exact solution in 1+1 dimensions. So again, this is a phase diagram which goes back to Thies and collaborators, and actually which has been known to the solid state community earlier on. So we have this translation invariant homogeneously broken phase, low temperature, low chemical potential, the chiral symmetry breaking for large temperature and large chemical potential. And here we have this new crystallic phase, which has been established rigorously in this limit NF going to infinity. Now, if you're in the crystallic phase, and if you increase the temperature and approach the phase transition line to the symmetric phase, what happens? That the amplitude of the condensate field goes to 0. And so you smoothly, so to say, the amplitude goes to 0 and you reach the symmetric phase without chiral condensate. On the other hand, if you go to the left and approach this phase transition line for a constant temperature at the critical mu, what happens is that the amplitude does not go to 0, but the wavelengths gets to infinity. And that is how you, join with a second order transition to a homogeneous condensate, which is not equals to 0. Okay, so this is the situation. And the question is, can we see anything like that in our simulations for a finite number of flavors? So So I had already, we have to study this model with this induced action. So the fermionic operator is neither Hermitian nor anti-Hermitian. So you should worry, of course, about the sign problem in the lattice approach. Now, 2 dimensions plus 1 plus 1 is sort of user-friendly. You can show that the determinant is real. It's actually also an even function in the chemical potential, and it's an even function in sigma. That just follows from charge conjugation symmetry and Hermitian conjugations. Now, this is true in the continuum. On the lattice, you can show this is also true if this operator here in the fermionic operator, this derivative operator, is anti-Hermitian and it's real. Okay. Now, this is certainly true for naive fermions, that this is a real and anti-Hermitian matrix. And the same is true for the chiral slack fermions. This again is a real and anti-Hermitian or antisymmetric operator. So what he did in our simulation, we used these chiral fermions, these slack fermions, and the naive fermions. And for those, again, this determinant is real. So if you take an even number of flavors, the determinant is non-negative, and you can do simulations. This means for slack fermions without the doubler problem, we can simulate 2, 4, 6, and so on flavors. For naive fermions, we can simulate, because of the doubler problem, we can only simulate 8, 16, and so on fermions. We did both the cross-check, right? For example, we did many simulations with 8 flavors, and then we could compare the slack fermions, results given by we got by the slack fermions with the naive fermions. And actually, there was complete agreement, right? So as far as you know, this simulation was really the first simulation for this type of model with chiral fermions at finite chemical potential and finite temperature. There have been long time ago simulation actually by Frischow, Karsh, and Korut and Wild, where you use staggered fermions as a 2-dimensional model. Okay, so there are different questions you can answer. In the 3D Turing model, the critical flavor number, in the 2D Gross-Neveu model, at finite mu and theta phase diagram, and maybe in 2 + 1 dimension as well. Okay, so let me be a little bit short. So again, we use these chiral slack fermions and the naive fermions. There is no additional sign problem. We have the sign problem we have in the continuum. We have the same internal symmetries that we have in the continuum theory, and we have no doublers. Okay, so first thing we have to do on the lattice, we have to set the scale. So what we do is we actually that just follows the analytical solution of the analytical calculation. As scale, we use the condensate at 0 temperature and 0 chemical potential. So we assume that for this point in the phase diagram, we have a broken phase, and use this sigma 0 to set the scale. Okay. So then all dimensionful quantities are given in terms of this fixed scale sigma 0. Then we generate ensembles on in G space. For example, the spatial grid goes from 31 to 128. And then we take different lattice spacing. The scale has been set, and that is how we define, of course, the lattice spacing to see how the results behave when we go towards the continuum limit. Okay, so let me mention here that in this type of models, there are these long-range correlators, and at the end, I hope I have time to tell you something about the behavior in the infrared of the correlation functions. So if you just do simulation and look for typical configuration, that's what you immediately get. That's actually what we got after half an hour or so. So there seems to be some structure. So here's time and here's space, and this is a typical configuration. Again, this was done with these chiral fermions. And you seem to see some sort of a kink-anti-kink structure here if you go in the spatial direction. And again, I should mention that this kink, anti-kink has been looked at by Fritjof and collaborators with staggered fermions, some smeared type of coupling to the fermions. Okay, so differentiate the homogeneous phase from the symmetric and inhomogeneous phase, which use sort of a condensate field. But then we cannot disentangle the symmetric from the inhomogeneous phase. So to disentangle these two phases, we use something, a two-point function of the order field, order parameter field, and actually also its Fourier transform. So what do we expect? Let's talk about the Fourier transform. If we are in the symmetric phase, so we have a homogeneous condensate, zero condensate, then we expect that has a small amplitude and no special features, the Fourier transform. If in the homogeneous broken phase, then we expect there's a peak at momentum zero, of course, because it's homogeneous. If in the inhomogeneous phase, we expect that this Fourier transform of the correlator has peaks at typically to momentum, and which defines the wavelengths of the inhomogeneous condensate. Okay, so these are some first results. This is this two-point function. The blue one is in the, you can see here the numbers. It's mu is 0 here. This is low temperature. So this is in the broken phase, homogeneously broken phase. Indeed, we see a constant C, and which is really essentially we use clustering, just tell that the sigma is constant here. And then in the symmetric phase, you see here this feature. If you go to the Fourier transform, again, what they said, you have essentially no special features in the symmetric phase, but you have a peak of the Fourier transform in the homogeneously broken phase. So this is now at again low temperature, but larger chemical potential. And here we see that we have a periodic structure of this two-point function. And just watch out, the blue one is the smallest chemical potential, and the green one is the largest chemical potential. And you see that the wavelength gets less if you increase mu. That's exactly what one has observed in the exact solution. If you go to the right in the phase diagram at low temperature, then the wavelength gets shorter. That you also see in the Fourier transform, the peak, they are more and more separated. When you separate more and more, if you increase the chemical potential, that this wavelength gets shorter. Okay.
5 minutes, please.
Yeah.
You have still like 5 minutes. Could you?
Oh, okay, good. Oh. Didn't we start at 10 past or 15 past 10? Okay.
10 past.
Okay, good. So here you see essentially the condensate field is this some related quantity. You can see here the homogeneous broken phase and the symmetric phase. If you just look at for the condensate field or related observables, we cannot disentangle the inhomogeneous phase. So then I again show you this correlation function C at 2 points, these red dots. And what this one shows you, the condensate, of course, you see the oscillatory behavior. This should also show you how this changes when you increase the number of lattice points and you go to the continuum limit. So the blue one is the slack derivative, and the other two are the naive. And the naive, you see, suffers from discretization effects. So if you go to a smaller lattice constant, then it approaches the slack result. Okay. So we see exactly the same feature as in the infinite NF limit, that the wavelength goes longer when you go towards the phase transition line. Okay, now we had these 2-point correlation functions. From this we can extract then the different phases. And this is a sort of a rough way how it looks like. So from left to right, we go to the continuum limit. From bottom from top to bottom, we go to the thermodynamic limit by increasing the number of lattice sizes here on the right. Okay, And you see that, that this unstable, this inhomogeneous phase, which is in blue here, almost doesn't move if you go to the small coupling constant and larger lattices. Now, 1 + 1 dimension is of course in particular tricky because of these no-go theorems. So the question is, what type of phase is it? Is it really a breaking, spontaneous breaking of translation invariance, or is it some sort of a long-range correlations a la Crosslevel? So we looked very carefully on large lattice for these 2-point functions and analyzed them as good as we could, and you know, try to fit it to a spontaneous symmetry breaking phase and to a Crosslevel phase. And it looks like it's really a spontaneous symmetry broken phase. Also, the analyses are not completely conclusive at the moment. Okay. So let me come to the baryon number, still staying in 1 + 1 dimension. This again shows you the condensate going to 0 at 0.5 chemical potential to this very low temperature. And at the same time, the baryon number goes up. Okay, at exactly the same point. That is again the baryon number. So there's a transition at mu 0.51. Actually, at large n, this transition is at 0.65, if I remember correctly. And I also we draw the green line, which is the exact result, but for adapted to the size of the system. And this dotted line are just free fermions, the baryon number. Okay. So now this is again is the exact solution. So what this shows here is actually deep in the inhomogeneous phase. The blue curve shows you the baryon density. Okay, so it's a modulated function, and the orange curve shows you the order parameter. So this is large n exact result, and so you see there's a clear correlation. Namely, if you square sigma, okay, the frequency then doubles, has exactly the same wavelengths as the baryon density. Okay, so in other words, if you want to know the number of baryons on the lattice, you just take the order parameter and count the number of oscillations. There's a 1-to-1 correspondence in the exact solution. Okay, so there's a clear correlation between the two. Question: does it survive for smaller numbers of baryons? And so again, the left-hand side you see the large n solution. On the right, you see the result of our Monte Carlo simulation. So what we show here is again this 2-point correlation function for 8 flavors. And what you show here is this correlation which we expect between the baryon number density and the square of the order parameter field, which has really the same. Okay, and we can calculate the same, of course, for the large n, and this is how the two compare. And you see they look very, very similar. So the finite NF resembles very much the large n result. Okay, now you can do even more accurately. You can define something like the dominant frequency. So what is it? You take this C, the expectation value of which was this 2-point function which we calculated. And for a given configuration, you can extract the dominant frequency, and then you average over the configuration. That is what we call this maximal frequency. That is where the signal on the average is maximal of the condensate field in this sense here. So in the large n, we would say this is equal to the number of oscillation. Okay. And it is the number of oscillations in the large n, and it should be related to the baryon number. So what you see here is this curve, the blue dots here, these are the Monte Carlo simulations, show you the baryon number as a function of the chemical potential at low temperature. And the orange dots are just this maximal frequency. So that they're really an obvious strong correlations. And you can see an individual configuration. If you go to look for the configuration, analyze the configuration as a function of the Monte Carlo time, you see there's essentially 1-to-1 correspondence between this baryon number and the maximal frequency. Okay, so let me conclude about this 1 + 1 dimensional simulation. So we have done the last 2 years in this Jena Frankfurt collaboration. First simulation with fermions at finite chemical potential, finite temperature, and a finite number of flavors. We studied very carefully 8 flavors, naive, slack, and the result degree. We studied carefully the 2-flavor model to study the infrared behavior of the correlation functions. And we also studied the system with 18 flavors to see how fast we approach the large N limit. Okay, so the phase diagram is astonishingly for NF equals 8, similar to the NF equals infinity phase diagram. And even for the NF equals 2, right, where the fluctuations are much bigger than for NF equals infinity or NF equals 8. And we have seen the inhomogeneous phase, but it gets smaller. That's expected, of course, because the fluctuation increase and they may destroy this, this inhomogeneous condensate. That's written here, okay? So there's a clear correlation between the baryon density and the condensate, and at least if the fluctuations are not too big at NF equals 8. And we have seen long-range correlation as expected in this 1+1 dimensional model. So what happens to the Goldstone models at NF less than infinity, still in the 1+1 dimensional model, is an interesting question, and we couldn't completely settle this question. We would have to look more carefully into the dispersion relation of the lighter states in these 1+1 dimensions, because there are theorems, there are statements evading the usual counting of Goldstone modes, depending on the dispersion relation of the low-lying particle, the would-be Goldstone bosons. Now we have done the first simulation in 1+2 dimensions of the Gross-Neveu model. So far, we haven't seen any clear signal of a inhomogeneous condensate. So in 1+1, we immediately got it, and then we carefully, of course, analyzed it. The situation is different in 1+2 dimensions. So again, if here is no special assumption about the condensate, it should come out of the simulation like it did in 1+1 dimension. But we haven't at the moment seen any signal of inhomogeneous condensate, at least in this Gross-Neveu model. Okay, there's of course a question then about the cutoff dependence, and we will hear more about by Mark. And what we are very much interested together with here in Jena with Michael Mandl and Julian Lenz, including external magnetic field, where we again have first order transitions in 2+1 dimensions. What about inhomogeneous condensate if you switch on an external magnetic field? Where the phase diagram, even the large M limit, looks something like here. So for a sufficiently large magnetic field in some units, you can have here sort of a first order phase transition, very similar like the 1+1 dimensional model. Okay, that I think time is over anyhow. So let me stop here. Thank you very much.
Yeah, thank you very much. Indeed, we are getting a bit late.
Sorry.
A natural discussion would be indeed on these no-go theorems and the Mermin-Wagner theorem and that. And so I would suggest to, if anybody would like to ask in this direction, to shift this to the discussion session. And I can only allow for clarifying questions right now, I think. So is there any urgent question about some clarification? So I see the same hand as usual. Mr. Macagliani.
You identified some inhomogeneous condensates, right?
Yeah.
In simplified models.
We did find, yeah. Mm-hmm.
Next question is, what are the excitations or collective quasi-particles on that lattice-like structures? I suppose that when you identify them and formulate effective theory, including excitations as local fields, you obtain renormalizable model. So in that sense, the renormalization is constructive. It helps to construct consistent theories, renormalizable theories.
Yeah, I completely agree. And lots is known about the particle spectrum in this model. There are baryonic excitations and the mass and many other properties of these particles are known. So you could proceed if you want, yes.
Okay, thank you.